Imagine a structure the size of a small neighborhood, alone in the middle of the ocean, shaken by waves, wind, and salt, while hundreds of people live there as if they were in a city cut off from the world. Now comes the strangest part. This steel city does not exist just to float, watch the sea, or serve as an industrial base. It exists to reach something no one can see, buried kilometers below the water, beneath the mud and beneath the rock. From a distance, an oil platform looks like nothing more than a metal tower lost in the blue. But when you look closer, it is almost absurd. It has living quarters, a kitchen, an infirmary, a helipad, cranes, generators, control rooms, emergency systems, and crews working day and night in precise shifts. It is an artificial island that cannot simply stop when the weather turns, when the sea rises, or when one part fails. And that is where the mystery begins. Because the most important part of this operation is not on the surface. What we see above the sea is only the visible tip of a much larger machine. Beneath it, an industrial pathway descends through the ocean, crosses the seafloor, and reaches deep layers of the earth, where oil, gas, and water have been trapped for millions of years. But think about it for a second. How can a machine built by humans work in a place where pressure is extreme, darkness is total, and any mistake can become an environmental disaster? How do you control something hidden inside the earth, under tons of water, without letting oil escape into the ocean? The platform has to generate its own power, receive supplies, protect workers, withstand the weather, monitor pressure, and keep everything running like an isolated factory. But it is not making an ordinary product. It is trying to bring an ancient, pressurized, invisible mixture to the surface from a place no human being can reach with bare hands. That is why, before understanding the machines, pipes, and valves, there is one question that changes everything. If there is no lake of oil down there, where is the oil really? Welcome to Invisible Structures. To understand how a steel city can pull energy from the bottom of the ocean without turning the sea into a disaster, subscribe to the channel, because this operation goes much deeper than it seems. The first big surprise is that oil does not sit beneath the sea like a dark lake inside a cave. That image is common, but it is wrong. Down there, what exists is far more curious. Rocks filled with tiny spaces, so small they seem invisible, holding oil, gas, and water, like a mineral sponge buried in the dark. It all begins long before any platform exists. Millions of years ago, microscopic organisms lived in the oceans, died, sank, and mixed with sediment on the seafloor. Over time, new layers piled up on top. Mud became rock. Pressure and heat transformed that ancient organic matter into hydrocarbons, while the planet's surface slowly changed. But forming oil is not enough. For it to accumulate, nature has to build an underground trap. First, there must be a porous rock, with internal spaces able to store oil and gas. Then, there has to be a sealing rock above it, a tighter layer that works like a lid. Without that natural lid, the oil could escape through fractures, spread into other layers, or never concentrate in enough volume. That is why a platform is not sitting above a hole full of oil. It is sitting above a very specific geological formation, rock with pores, trapped fluids, pressure, and a barrier capable of holding everything there for ages. The visible part of the operation begins in the platform's steel, but the reason everything is there lies hidden in deep rock, below the seafloor. And there is another detail few people imagine. Even when engineers find the reservoir, that does not mean all the oil will come out. Some of it sticks to the rock's pores, trapped in narrow channels, mixed with water, or too far from the main flow. Extraction is not like emptying a tank. It is more like trying to pull liquid out of a stone filled with microchannels. Before any production begins, seismic studies try to map the subsurface using reflected waves. Geologists interpret hidden layers. Engineers assess whether there is enough oil, whether the rock allows flow, whether the pressure is workable, and whether that point in the ocean is worth turning into a multi-billion-dollar project. One mistake can mean weeks of work, millions spent, and almost nothing found. The most impressive part is that this entire operation depends on a calculated bet on something no one sees directly. The platform, with its cranes, pipes, and control rooms, exists because somewhere below the sea, there is rock capable of holding ancient energy inside microscopic pores. So the question becomes even more delicate. If the oil is not in a lake, but trapped inside deep rock, how do engineers create a safe path to it without opening an uncontrolled door for the pressure to escape? And if this discovery about the oil sponge changed the way you see the sea floor, hit the like button. It helps invisible structures reveal more systems that almost no one ever sees working. If oil is trapped inside rock, the platform has to do something extremely delicate. Open a path to it without turning that path into an uncontrolled crack. It is like trying to drill into a pressurized box in the dark from kilometers away, while still making sure nothing escapes through the wrong place. That path is the well. Drilling begins with a bit descending toward the sea floor. It spins, grinds through layers of sediment and rock, and advances little by little, while a special fluid circulates through the well. This fluid, known as drilling mud, helps cool the bit, carry rock fragments back up, and balance part of the pressure coming from the depths. But the well is not simply left open. As drilling advances, steel pipes are installed inside it, as if the industry were placing an armored straw through the earth. Then cement is pumped into the space between the pipe and the rock. That cement hardens and seals the path, preventing oil, gas, or water from migrating outside the pipe. This is one of the most important ideas behind why oil does not just leak out through the seafloor. The well is built in stages. Drill a section, line it with steel, cement it, test it, and only then keep going deeper. Each layer must withstand the pressure, the temperature, and the fluids found along the way. During this phase, the most important word is control. Down below, the reservoir can push oil and gas with enormous force. If the internal pressure overcomes the well's barriers, the flow can rise too fast. To prevent that, the platform monitors signs all the time. Changes in fluid volume, pressure increases, return speed, and the behavior of the drill bit. That is why a gigantic piece of equipment is installed on the wellhead during drilling, the BOP. It works like a set of emergency valves. If something goes out of control, it can shut the well, seal the space around the drill string, and, as a last resort, cut the pipe to stop the pressure from advancing unchecked. It is heavy, expensive, and vital, because it works right on the edge between engineering and disaster. After the well reaches the producing zone, it still has to be completed. That means preparing the final connection with the rock holding the oil. In some cases, small openings are made in the casing to allow oil and gas to enter the well. It sounds simple, but every hole, every valve, and every test determines how much fluid will enter and how safely. When drilling ends, control changes hands. The BOP is no longer the center of the operation, and the subsea Christmas tree takes over, a set of valves installed on the seafloor. It does not have that name by accident. It looks like a structure full of metal branches. Its job is to open, close, regulate, and monitor the flow leaving the reservoir. It is what allows production without letting the well behave like an open hole. The oil only rises because there is a defined path, lined, cemented, tested, and controlled. It is not the platform ripping oil from the earth by brute force. It is a constant negotiation with the pressure hidden inside the rock. Even so, a platform rarely depends on a single well. On the ocean floor, there may be several production points spread out, each with its own wellhead, valves, and behavior. Now the question changes scale. How do you turn several separate paths into one system, monitored and connected to the surface? And to follow how this well stops being an isolated path and becomes part of an entire network on the seafloor, subscribe to Invisible Structures, because the next part reveals the structure almost no one imagines exists beneath the waves. When a well begins producing, the operation is no longer just a line descending from the surface. On the ocean floor, several separate points have to work, as if they were parts of a single machine. Each well has its own pressure, its own mixture, and its own behavior. One may bring up more gas, another may produce more water, another may have a stronger or more unstable flow. That is why production cannot simply rise any way it wants. Before reaching the platform, these wells have to be connected, organized, and monitored. That is where manifolds come in, large metal structures installed on the seabed. They work like industrial intersections on the ocean floor. Instead of cars, mixtures of oil, gas, and water pass through them, coming from different wells. The manifold receives these flows, directs production, and helps control where each line should go. From there, the mixture travels through subsea pipelines. Some connect nearby wells, others run long distances to a platform or a floating production vessel. These lines must withstand the external pressure of the water, the internal pressure of the fluids, corrosion, cold, and the ocean's constant movement. And there is a silent danger on this journey. In deep water, the temperature is very low. If the mixture cools too much, certain compounds can harden, form deposits, and block the passage. So the platform controls not only how much oil rises, but also the temperature, pressure, and behavior of the fluid inside the lines. For production to reach the surface, risers come into play. Large vertical connections between the seafloor and the platform. They work like industrial arteries. Inside them, the mixture rises. Outside them, they face currents, vibration, weight, and motion. One failure along this path can halt an entire operation. Since no one can walk through this submerged installation, Part of the work is done by ROVs, remotely operated robots. They descend with cameras, lights, mechanical arms, and tools. They film valves, check connections, inspect pipelines, and can turn controls located hundreds or thousands of meters deep. Meanwhile, sensors spread throughout the network measure pressure, temperature, vibration, and signs of leakage. In the control room, this data appears like the vital signs of a hidden city. A small change can indicate a blockage, a valve failure, or a shift in the reservoir. And this network is not only used to extract oil. In many fields, water or gas is injected back into the rock to maintain pressure and push some of the oil toward the producing wells. The seafloor becomes a system of circulation, collection, and balance. The visible platform is only the entrance to this structure. Beneath it, there may be a web of wells, valves, pipelines, robots, sensors, and flow lines working in silence. But when that mixture finally reaches the surface, it is still not ready to be sold. In fact, a new stage begins there, separating oil, gas, water, and impurities inside a floating factory in the middle of the ocean. Comment what surprised you most about this underwater city, and also tell us where you are watching from, because it is fascinating to see where the invisible structure's audience follows these hidden systems from. When the mixture reaches the surface, the most delicate part still is not over. Because what rises from the seafloor is not finished oil. It is an unstable combination of oil, gas, water, fine sand, and salts, all arriving under pressure after crossing kilometers of rock, pipelines, and subsea control. If it went straight into a ship or pipeline, it could corrode parts, form blockages, reduce efficiency, and even create operational risk. That is why the platform also works as a floating factory. The first mission is to calm that stream and separate the fluids. Inside large metal vessels, called separators, production enters at controlled speed and begins to divide. The gas, being lighter, rises. The water, being heavier, sinks. The oil stays in the middle, still needing treatment before it can move on. This separation depends on time, pressure, temperature, and the internal design of the equipment. Some parts change the fluid's path, others reduce its speed. The goal is to give each component a chance to separate as safely as possible, without interrupting production. The gas can have several destinations. Some of it powers turbines and generates energy for the facility itself. Another portion may be sent through pipelines when there is a route to shore. In many fields, it is re-injected into the reservoir, helping maintain pressure down below. So the gas stops being only a challenge and becomes a tool for pushing more oil toward the wells. The water also demands care. Because it passed through the rock and came mixed with oil, it must be treated to remove residues, oil droplets, and impurities. Depending on the operation, it may be discharged under controlled environmental limits or re-injected underground. Nothing there is simply thrown away without monitoring. The oil then moves through new stages. It has to lose part of its water, reduce impurities, and reach the right condition for storage and transport. In many cases, this happens inside an FPSO, a floating production vessel capable of producing, processing, and storing oil inside its own hull. While equipment works on deck, enormous volumes of oil can remain stored in internal tanks, waiting for the right moment to move on. Then the shuttle tankers arrive. They approach in carefully controlled operations, receive the cargo, and carry the oil to onshore terminals. In some projects, production moves through pipelines. In others, building a line all the way to shore would be too expensive, too long, or too complex. That is why storing oil at sea and transporting it by ship can be the most efficient solution. This is the point where the isolated structure in the ocean connects to the real world. Energy leaves a porous rock, passes through the well, crosses the subsea network, rises through the platform, is separated, treated, stored, and sent into a chain that continues through refineries, roads, airplanes, ships, machines, plastics, and asphalt. The platform is not the end of the story. It is the first visible point of a system that begins hidden beneath the seafloor and ends spread throughout modern life. What seemed like only a steel city in the ocean is actually the entrance to an invisible chain that transforms rock, pressure, and millions of years of stored energy into fuel for the modern world. If this video made you see this structure differently, subscribe to Invisible Structures and comment which part changed your view the most. The well, the underwater city, or the floating factory?